LCR circuit in series. When a resistance, an inductance and a capacitance are connected in series as shown in figure, across an AC source, the same current would flow through each element. The flow of current through the resistor develops a voltage ER equal to I into R in phase with the current. The current through the inductance develops a voltage EL equivalent to I into XL, and that leads the current by 90 degrees. The current through the capacitor establishes a voltage EC equivalent to I into XC, which lags behind the current by 90 degrees. All these quantities are represented in the vector diagram with their respective phase relationship as shown in figure. At higher frequencies, the circuit is more inductive in nature. Please note, inductive reactance is greater than the capacitive reactance. At lower frequencies, the capacitive reactance Xc is greater than the inductive reactance. The resultant reactance will be capacitive in nature. Series resonant circuit. An interesting frequency is encountered when the inductive reactance XL becomes equal to capacitive reactance Xc. The reactive component becomes 0. XL minus Xc is equal to 0, and Z is equal to R. The circuit becomes pure resistive. This phenomenon is referred to as resonance. The frequency at which resonance occurs is called the resonant frequency F0. Hence, the resonant frequency F0 is equal to 1 over 2 pi square root of LC. The circuit current I0 would then become E over Z0, which is equal to E over R and is maximum. Thus, if an alternating voltage of frequency F0 be applied in series with LCR circuit, then the value of resistor is fixed. We see that Z0 is of minimum value, and hence the current reaches its maximum. It is perhaps surprising that the frequency for maximum current, resonant frequency, is independent of the circuit resistance. The state of maximum current flow is called series resonance. The voltage across the inductance and capacitance are equal and the opposite sign, thus cancelling each other. But usually they are large compared to the voltage across the resistance. The ratio omega naught L by R, usually denoted by Q, is the ratio of reactance of the coil at resonance to the resistance in series with this. This is called the magnification factor or quality factor. The voltage across coil or capacitor will be Q times the supply voltage. Q, the selectivity can also be obtained from Q is equal to F0 over 2 delta F. Refer figure.
Here, in this experiment, we demonstrated the functioning of series resonant circuit. L, C and R are connected in series across the waveform generator set at sine wave mode. Output of the sine wave generator has been set at some arbitrary level. Inductance has been precisely wound on a powdered iron core to the value of 100 millihenry. Capacitor used in a non-precision type value 1000 PS or 0.001 microfarad. A low value resistor of value 10 ohm is used to obtain high circuit Q. No doubt, this low value 10 ohm resistor would throw a heavy load on the waveform generator, resulting in the drop of its output voltage. This is expected. We have no alternative but to obtain high Q through this low value resistor. The frequency of the generator is carefully and slowly varied towards the calculated resonant frequency of 16 kHz. Measuring the voltage across the inductor or capacitor at each setting. As we approach the resonant frequency, a sharp increase in output level across L is noticed, giving an indication of resonance. Very cautiously, the frequency of generator is set at resonance condition. The output voltage across the capacitor has been measured to be around 112 volt, fantastically very high level. The supply voltage has been measured as 1.25 volt. Thus, the two continue. The resonant frequency is obtained from the dial setting of the sine wave generator as F0 is around 118 kHz. We have to acknowledge the deviation from the expected theoretical calculations, as there are many unavoidable inaccuracies in this experiment. EL is equal to QE. EC is equal to Q into E. ER is equal to E. And Q is equal to EL by EE. In this case, it is more than 100 times.
Parallel resonance. Let us now examine the result of applying an alternating voltage E across the condenser C and an ideal inductance L without any loss resistance. Figure that follows shows the arrangement of parallel resonant circuit. The source supply divides between the two branches, and we find that the RMS value of current in L is given by IL is equal to E over XL. Similarly, the RMS value of current through the capacitor C as IC is equal to E over XC. Adding the two currents with due regard to their phase relation, the RMS value of the total current I is found to be I is equal to E over Z. Resonance occurs at a frequency F0 when XL is equal to XC. At this stage, IL is equal to IC and the resultant current IL minus IC is equal to 0 will be practically 0. Figure shows the vector relationship between the inductive and capacitive currents, which differ by a phase of 180 degrees. A fairly large current would be circulating through the parallel LC circuit. The current drawn from the input supply would be the supply current I is equal to IL minus IC. Refer the vector diagram. Thus, at resonance, practically no current is drawn from the input source, even though large currents are circulating through the LC circuit. The parallel resonant circuit acts as open circuit at resonant frequency. It offers low impedance at frequencies on either side of resonance. Note, Z0 will be very high in value. Resonance occurs when XL is equal to XC, that is omega naught L is equal to 1 over omega naught C. Therefore, F0 is equal to 1 over 2 pi square root of LC. However, in a non-ideal coil, a small loss resistance R is to be added in series with the inductance. In such state, a small current would be drawn from the AC supply. IL is equal to IC, which is equal to E over omega naught L, which is equal to E into omega naught C. And it is Q times larger than the current in the external circuit. It is assumed in this work that the capacitance loss is negligible and has not been considered seriously. At resonance, it can be shown that the current I in the external circuit is I is equal to E over Q omega naught L. The factor Q into omega naught L is to be regarded as the high resistance value offered by the parallel resonant circuit. Accordingly, it is designated as the dynamic resistance RD. Thus, the parallel resonant circuit becomes an ideal tuned circuit. And this finds extensive applications in tuned amplifiers and oscillators.